of V, the coefficient of consolidation. And that analysis involves some graphical construction, identifying points on the curve, and determining from that a small t50, a small t90, which are real times, typically in minutes for laboratory data. And you use that conventional equation with H drainage squared, big T, little t, and so on included in that, which we'll be doing quite a bit of in the class. Not too much graphical construction. You'll have an opportunity on homework 5 to address that once, but you'll use that equation a lot when applying it to field data. So that shows the example where you're applying it to lab data. Oftentimes right away you do a flip and you apply that value then, which is a soil property, to a field situation to assess how long will it take, for instance, for 90% of this consolidation to be completed. That's a common type of calculation that would be applied in the field. We also looked at, oh boy, that's not behaving, secondary compression. And that assesses a creep mechanism in soils, which would be a continual compression occurring, assumed to occur after end of primary. So after that little knee in the curve that is showing up on a void ratio log time plot. And the slope of that does show up as a C sub alpha. The equation associated with that has a very similar format to that of magnitude of settlement, because it's a semi-log plot associated with void ratio on the y-axis. And it would just be time is what's going through the change. And the fraction that you have, log of a fraction, is still endpoint over starting point, except now we moved on to a time domain instead of a stress domain. And in that mode, you would commonly have an endpoint being something like 50 years or, some design life over the starting time would commonly be established as an end of primary. So you'd have some assessment for that. Today, I'd like to look at reinforced concrete design. And we may get through most of the content today, but I'm not going to crush it in and try to have a ridiculous schedule to do so. We'll see how progress is going, and I may even cut at a portion of the lecture and leave some of it for next time intentionally to let some group work go on the final projects. I really think that's an important component of the course at this stage, and want to give you some working sessions. I'll call it plural at the moment, either today, but most certainly we'll have some time next time to get into that. So my intent would be a facilitated breakout group action where you have some time with your group to try and make some progress, and I'll be around, bouncing around between groups and available for Q&A, and see how that is going along. I do not discount the magnitude of that assignment at all. I understand it's a big one. It is comprehensive of the entire class. So I'll say if you can get that knocked out and feel comfortable, you're all set in the class, for example, for the final exam, meaning very little additional study would be required if you feel comfortable with the content in the design project. So I would like to take a look now at some reinforced concrete aspects. And I'll begin here with let me make this a little bit larger so you guys can see it better. There we go, that should work. And I'd like to provide first an overview of the approach. And I have several steps identified here. And I'll have a refined version of this list in a handout for you in just a moment that I'd also like to run through. But this is kind of the whole deal, including some fairly minor steps that would be included. First off, before we get too far on that, are there questions on the secondary compression or time rate of consolidation material at this stage?
How similar of values are we supposed to be getting for C sub V between the T50 and T90 values?
I would think they could vary considerably. I wouldn't expect orders of magnitude, but you know, uh, a factor of two or a factor of 1.2, something like that, wouldn't surprise me at all. So,
Okay.
uh, and you'll be determining that. There is a question mark at the end of that of which value do you actually run with, which do you take and use for design purposes. And I'll provide a little context here on that point. It commonly is taken as the T90 method. And that's because it leads to a faster uh, T90 in the field. And that is assumed to control because Tertsagi's theory is very idealized. It's assuming, if you recall, only one-dimensional flow, up and down. That's it. And in reality, you actually have water sneaking out to the sides and so on. And you have the presence of macro features, which would be present in a real soil deposit at field scale, where sand, a little fissure filled with sand might be available, and water pressure can dissipate through such a crack. And when you have a little 3-inch specimen, a little hockey puck in the laboratory, and you're running consolidation tests and then analyzing it for T50, T90, you don't capture that at that scale. So, in fact, the lab captures neither of those features, the three-dimensional element of it sneaking out the sideways or macro features. So because of that, it is commonly taken that you would evaluate using the version that would provide a lower value of T90 at field scale. I'd like to get back to the reinforced concrete overview. And as a first step, you would factor your loads. And this is typical structure stuff. And hold on here. And 355 is concrete, is that correct? Okay. Just bear with me, I'm trying to set up a poll here. I'm not able to do this very efficiently today. This isn't falling into place. What I'm trying to do is set up a poll to simply ask, and I can do this in person, probably much easier. How many of you have had 355 concrete design, reinforced concrete? If you could just show with a hand or some kind of symbol. Okay, looks like a bunch. Maybe half-ish. Okay, or a little more, half or a little more, it appears. So it is not a prereq here. You do not need it to deal with this unit. I just want to be extremely clear about that. I will lead you through step by step, but I just want to get a flavor for, a history in this material coming in, as, you'll have a little different take on it, of course, if you've had that entire course. And my understanding with the curriculum of 355 is that concrete design for shallow foundations is not covered, and I expect that has not changed in recent years. So this is a nice addition if you've had the course to see this content as well. So I think it will be neither redundant nor daunting, regardless of your background. So first up, we're going to factor loads, and this is an uptick on the loading scenario, dead and live loads. And you can have wind loads, snow loads, all sorts of loads can come into play. And they'll each have different factors associated with them. And I'll apologize ahead of time today for some of the notes having a little bit of this light colored material here with a light gray seeming text. This was a set of notes in pencil. I scanned it in, and a few of them just turned out rather light unintentionally. In any event, what you do here is you come up with an ultimate load. And as I mentioned, it's an uptick. You're kind of elevating or inflating your load for design purposes. And you do so as a function of uncertainty. And there's most certainly a higher degree of uncertainty with live load than there is with dead load. With dead, you have a very good feel for what's going to be in a building. It will be a certain amount of furniture and a certain amount of books and so on. And that depends certainly on the function of the building. I mean, a library is going to have a heck of a lot more dead load than would an empty office building. But there would be some standards that you could apply to this and get some estimates. But in any event, you will have, in the end, dead load that you'd be working with. And that would be the material that stays in place. And this will be a lower factor that's applied because it is quite certain what that will be. There's not a great deal of variability, whereas a live load can be all over the board, and you really don't have a feel for what that's going to be. It can be a question mark even for the future. And I check, football occasionally for my alma mater, the University of Wisconsin, the Badgers, and they have a tradition there in the third quarter to do what they call the jump around. And it's a tradition that started, I don't know, 8 years ago or something like that, where they play a certain song and the entire stadium literally jumps in sync to this music. It's remarkable in a sense. It's great fun, but also, and rather entertaining. The TV always shows it and so on. But that wasn't known at time of designing that structure, that would be going on. And this is an example of the uncertainty of live loads. Things can happen that you just don't plan for in this. So therefore, it's inflated more to account for that uncertainty. At the same time, we're going to reduce the strengths. There's reduction factors applied for strengths. And that reduction factor is called a phi. And I think you'll be able to keep track of when we're talking about a structure's reduction factor and when we're talking about an angle of internal friction in the class. They are the same term. That's just, by coincidence. And that phi ranges from 0.65 to 0.9, depending on the strength condition. If it's shear or so on, if it's bending and this kind of thing, you'll have different conditions to account for workmanship and the actual value used for the strength. And I'll have a table to share with you that identifies all of those, and we'll go through them in an example. I've mentioned repeatedly in here that we'll be going through this whole thing by example. And this is establishing your loads. So this is using load resistance factor design, LRFD. And with soils, we're not using that, just to stay straight, that we have two analyses going on somewhat concurrently. And we're using a working stress design for the soil part, where we just apply a single factor of safety at the end. And that's how the geotech stuff is handled. Whereas the structure stuff has this going on, where you're both inflating the load and reducing the strength. And that is in disguise a factor of safety, a rather refined one. It's in a sense more refined than just applying a 3 at the end of the problem. Next up, we're going to design the thickness of the footing, and we'll do this based on shear analysis or shear mechanism of through the concrete. And we'll be looking at two-way shear, because we'll be designing a square footing. I'll show you the one-way shear just for a kick, so you have it in your notes and you understand what that is. And that does come into play on rectangles and strip footings. So, it can have certainly a use. But if you're looking at squares, and that is what I'll hold you responsible for in the class, it would be two-way being controlling. Next up, you will design reinforcement steel. And the reinforcement steel will be based on a critical section, and we'll identify that critical section using a cantilever. And that cantilever is going to be extremely simple statics application. And this entire, you're seeing this handout, correct? Good. Okay. I think I have the whole desktop today highlighted rather than just the handout. And I'll probably change that as we go along, but just a few more items. I'll stay with this view for the moment. Next up, we'll establish the development length for the steel. How long does that steel have to be in order to have enough interface between steel and concrete to develop that strength that will be required for serving in tension? We will determine transfer forces at the base of the column, and that utilizes a geometry called a frustum. It's an oddball shape that I'll share with you in a little while. And you will determine the compression steel and development length. That's quite straightforward. That's more or less some rules are applied, and it must be at least this, and very simple step. We'll have cover for corrosion protection. That just means you have a 3-inch cover everywhere. You have 3 inches of concrete to prevent the steel from going through any kind of corrosion and exposure to the atmosphere or elements. And then you will draw a final design sketch, and I'll share with you an example of that. So that is the kind of full list of the detailed list of what approach we will be utilizing here. And I'd like to run through an example with that. But before I go through the example, I want to share with you two handouts that are available on our Canvas site. One is a short PowerPoint presentation with just a couple of images. I think they help a good deal of describing some of these geometrical configurations I'm alluding to. And another is a handout that has some appendices from a structures text, the concrete book that's used at Cal Poly, by the way, and at least was as of a few years ago. I think it was last updated when the code was updated is when I've provided update to that example. And I'd like to look first at that PowerPoint. So this is the reinforced concrete design for footings, and I would like to share with you the steps again, but this is kind of a refined version, not getting down to nitty-gritty of factoring loads and so on, but hitting the main components of shear, column bearing, bending, and connection detail. So those are the big items that would come into play on reinforced concrete design for footings. And the rest is quite minor stuff, but it's also, you know, part of the process. You'll be seeing it in the example and incorporating the whole set of steps. But these are, I'd say, the big ones, the conceptual ones. Punching shear failure is what would be anticipated to occur for a single footing. And I have a square footing shown here with a column, and this would be the anticipated shape of shearing of that column punching through that footing. And what we need to do is design the thickness of this footing, the height of it, in other words, height of the pad, such that this doesn't occur. And that is the task at hand. And this geometry is quite complicated mathematically to deal with in structures analysis. So what's going to happen is a simplification of this. And that simplification looks like this. Now we're looking down on that footing, and it happens to be rectangular. I mentioned square, but here in this view, we're seeing a rectangle version. And it is simplified that instead of being a 45-degree angle coming off of this column, it's actually a simplified, I'll call it a cookie cutter version, running right on through the pad of the footing. Oh, excuse me. So instead of this shape where it's 45 degrees, we're going to identify some intermediate point out here, a square that's around the footing that's larger than the column base. That would be, you know, nominally something like halfway out here. And it's going to have vertical sides, and that will represent our shearing surface. And that's considerably easier to handle mathematically in the equations and solve for than dealing with this, you know, pyramid type structure shape of punching through with an angle like this. So we have an ABCD shape that is identified outside of the footprint of the column. And we have a D over 2 identified here. Excuse me. And D is going to be indicating for us the height of the column, the height of the footing, by the way. Let me back up and show that. This will be D, the depth of the footing. And that will be from the top of the pad down to the reinforcement steel. So there's still going to be a little bit of concrete down here, which is considered cover. And that cover is not considered in this design. That would be gravy. It's a little bit extra capacity, so that's all good. But it is not included in the calculations solving for shear. So D over 2 means that this rectangular shape around the column is indeed halfway out on that pyramid type structure. And we also have a D identified here as the possibility for shear. And this would be the two-way shear all the way around, and one-way shear would be something out here, which would be D, distance away from the column. And again, we will, in this class, for square footings, this will always control the inner version, which is a shape around the column. These are posted on Canvas, so don't worry too much about, details and reproducing everything here in these graphics. I'm just trying to give you the big picture so you have it in your heads before we get into the numbers. And this would be critical sections for bending, and they are going to be across here and across here. It happens to be that it would be a cantilever type section. And I'll show you the equations for that as we go, but the statics are extremely simple. It just ends up being like a beam with a distributed load on it. That distributed load happens to be the reaction of the soil pushing back on the footing is what it is. But the equations you've most certainly seen before in some lower level mechanics type courses. This is the frustum shape. So this is now checking the bearing of the column onto the footing. Is there going to be a localized little punch out going on? And what we have to do here is identify this 2-to-1 or 1-to-2, as it might be called, using the geotech terminology to be consistent with what we spoke of earlier in the class. Because, by the way, this is different than what we assume is going on in soils with that 2-to-1 method. And we will establish that shape of having an area of the footprint of the column, and then an area down here, which is measured at the largest plane that can be fit within, that frustum shape. And the frustum gets cut off here because this hits the edge of the foundation. So right there, that defines the bottom of the frustum, and by definition, you would then draw a horizontal here and say that's it. And from there, you will measure an A2, which would be looking down on the footprint of that area A2. And we'll look at an example as we go along. And this would be an example of a design sketch. So this will be included in the steps and will be incorporated into your design project. So I'm looking for something of this kind of detail. It's not tremendous detail, but it includes the critical information such that a foundation could be built to spec and identify main things. So I would expect this day of age that you'd be producing this in, say, AutoCAD. I think it would be easier to do it there than by hand. But if you do it by hand, it's something that I can offer full credit for. If done, I'll call it properly from a drafting standpoint, that you'd have drafting tools out and making it clear, clean, precise, and so on. Absolutely, that would be acceptable. I'm not forcing that you use AutoCAD, but I would highly encourage in this day of age that you would be using AutoCAD. And that is it for the overview. Are there questions on any of those images? Let's start there.
What's the difference between the frustum consideration and the punch-out shear failure consideration? They look like they're looking at the same kind of shape of
They kind of
in
are. The frustum is dealing with just that, the end bearing actually punching into the concrete itself on a very localized basis, just having the column crush into the concrete. And the shear is speaking much more generally about the entire section being failed and the entire column going through the pad of the footing, and a complete structural failure through the entire depth. That would be the key. So there could be a chance of, if this is off near the edge, kind of it crumbling and so on. And there is a check in place for that sort of thing. I hope that helps. Other questions? Okay, I'd like to run through, as I mentioned, the handout that I have, which is straight from a textbook. So this is just straight on copy of the text to help you out. It's mostly appendices from that book and kind of go-to information. It's a set of tables, it's a set of charts and so on that you can use to identify key parameters, mostly tables, I should say. And what we have here is a description of the main concept that you would have phi mn being less than mu, or greater than mu, I'm sorry. And the same thing with phi vn. And we'll get into those as we go along. The factored loads are identified here. And my expectation in here would be the basic approach. I'm not trying to turn this into a structures class. I'm just trying to have exposure of this topic for you. And the 1.2 and 1.6, I think, will hold us in here. But you do see in this case that you can have snow, rain, temperature, wind, earthquake, a lot of different features and different combinations of those types of loading, such that you'd have different ultimates for those different types. Strength reduction factors. I mentioned that they range from 0.65 up to 0.9. So this is a reduction in the strength that would be counted on for given components in your structure. And they're going to vary whether you have a tension controlled section, compression controlled section, a shear and torsion, bearing on concrete, and so on. And I'll lead you through by example what are kind of the takeaways here. I'm not just going to throw you in the deep end on this stuff and say, go figure it out. And we'll go through that example, and realistically, if you can follow that, you'll be responsible for changing numbers in that example, more or less. So the steps will be laid out quite cleanly for you. This is the behavior, big picture behavior of reinforced concrete under increasing load, and highlights really the elegance of this material as a construction material. It really is a cool development in the structures area. That it represents by all means a composite material, that you have concrete and steel acting on the bottom quite commonly. And that steel can also, for some applications, be running across the top. And it's shown here acting on the bottom for good reason, that this is an example of flexure, a conventional flexure. And the flexure that we're speaking of here is something like this. So it's a beam that is going through loading that would bend it like this. And if you do this with your hand, you're going to find that the skin on top of your hand crinkles up, and the top of your hand is in compression, just like the concrete in that beam. The bottom of your hand is getting stretched, and you can feel it in the skin. And Concrete goes through the same thing. And so we have compression on the top of a beam, inflection, and tension on the bottom. And how do you resist that? Well, concrete is a fantastic material in compression. It's quite lousy in tension. Steel, on the other hand, handles tension very, very nicely. And, hit and miss on compression depending on slenderness ratio and so on. But in any event, with this design, you have an opportunity to count on compression, count on concrete for compression loading by having it up here, and count on steel for tension. So steel is going to carry the tension load by being located down in this region, and concrete is going to carry the compression load by being located up in this region. And we can identify the strains associated in cross-section through that type of section. And this is showing quite an extreme example where it's actually cracking and showing that lousy performance of concrete in tension, but the steel is there to hold it together, so it's not horrible yet. And if we look at the response to this, we find that the steel is in tension, holding that just fine. And in compression, you have a distribution of compressive forces that looks something like this. It is a parabolic type distribution. And this can be, I think we'll see a better version of this in the next slide. We do. In which this is the actual loading that would occur. You'd have a number of, or a wide steel bar down here, or a couple of bars as it may turn out. And that would be the tension. And this up here would be the compression forces acting in this parabolic type distribution. This dashed line across here is called the neutral axis. And that's where there'd be a crossover from compression to tension in that section. This, similar to that oddball pyramid shape in shear, is difficult to handle mathematically for solution in simultaneous equations and so on, and trying to sort out what's the thickness of a section needed or how much steel is needed would be the question at hand here. And we will need to mimic that somehow, and something called a Whitney stress block was developed that looks like this. So it's a simplified version in which this dimension A is defined, little a, is the height of that Whitney stress block. So we'll be looking at this as we go along, but the idea on that block and the parameter little a is that that whole shape is representing this more complex actual shape that is going on. Next up, I have some hooks shown. And what we're going to find is that bars are going to be inside the concrete. And the bar may be responsible for holding a certain amount of tension or compression for that matter. And in order to develop that, in order to mobilize that force inside the bar, it actually needs to have interaction with the concrete. And therefore, it needs some length in the concrete to do so. So we're going to define some minimum development lengths. And when we do that, you may find that the geometry of your pad of your footing simply doesn't permit there to be sufficient development length. And if that is the case, you will develop something called hooks. You just bend the bar around and force it into that geometry where now you have a longer length allowed in that geometry. And for this class, where I'm going to draw the line is to determine for a section whether or not you need hooks, and simply indicate clearly in a solution if you do need hooks. And that's it. I'm not going to have you get into designing hooks. This shows a little bit of the design for that, where you would have, diameters associated with this, minimum diameters for this. And here's the table showing those minimum diameters. The diameter of a hook is going to be a function of bar diameters, as it turns out. And then you have different geometrical configurations and so on. And we're not going to get into this kind of minutia of the structural design, but I thought it was helpful for you to see this, just so you see where this material is going, and that, hey, there are design steps beyond what we're considering. But be aware, we will get to a stage of saying needs hooks, and that there are then steps to refine that. But I don't plan to explore that and turn this into 3 weeks of content. So for this shear, we have seen this graphic already in that slide presentation. And the design aids are in this appendix. And there are, first off, diameters and cross-sectional area and nominal weights of different bars. And as it turns out, inch-pound bars, reinforcing bars, that is steel bars, are set up where the notation is eighths of an inch. So 3 means it's 3/8 of an inch diameter. A 4 is a ½ inch diameter, 4/8. An 8 means it's a 1-inch diameter bar. SI, on the other hand, System International, is based in millimeters. So this is a 13 millimeter bar, nominally a ½ inch. 25 millimeter bar, nominally 1 inch, so in line with the 8. And this tells you the diameter of those in inches, cross-sectional area in inches squared, and nominal weight of those bars as well. And you can get into some fairly hardy diameter bars, as you see, approaching more than 2 inches. So that's a fairly robust reinforcing bar. This next one is area of groups of standardized bars. And this is a table that shows us the bar number in both inch, pound, and SI. And across here, the number of bars. And that'd be in a collection. Just, we're going to be searching through this table, and that's just the total number of bars. It could be number of bars in a footing. It could be number of bars per linear foot of a footing. There's different ways to be designing this, and we'll look at that a little bit when we get to the example. And therefore, we have small bars and low number of bars off in the left corner, and large bars and high number of bars down in the lower right corner. So the numbers tend to migrate towards higher numbers as you go diagonally from upper left to lower right on this table. And what we're going to do here is fish around this table and find some minimums that we're searching for. We'll get to that. This is areas in slabs. This would be limiting steel reinforcement ratios for tension-controlled members. And this gives us a strength of steel, tensile strength of steel, Fy prime. We have a strength of concrete, compressive strength of concrete, Fc prime. And you see that there's a tremendous range on that, going from 3,000 up to 9,000 psi. As it turns out, footings are designed with relatively low strength concrete. And can anyone think why that might be? Why would you actually want to have low strength concrete in a footing as compared to a column, for instance?
The footing's primary purpose is to transfer the load to the soil, and so if it's much, much stronger than whatever the soil strength is, it's kind of redundant at that point.
There's a redundancy that Evan is pointing out. Any other thoughts?
If the concrete fails before the steel, it'll be a slower failure. Isn't that kind of where you're going there?
There is that element as well, that there tends to be, if your footing fails before, for instance, the column, it will provide a more ductile type failure and a warning of impending failure. So you start to have some movements in the building and you understand that, hey, there's some trouble here, time to evacuate, and you have a warning system kind of built in to your structure with that. And that would be the primary reason for having low strength concrete in footings, relatively low strength. And then we'll have some row minimums. And a row is a ratio of the area of steel to the area of concrete. And we'll look at that with the example. There's also a development length. That's going to be a function of concrete strength for some different strings here and different ranges of bars. So this would be number 6 and smaller, or number 7 and larger, 2 categories. And then we have bottom bars and top bars. And the reason, by the way, you might have top bars on a footing is that you could consider having a mat foundation where you have multiple columns coming down onto a given pad and soil pressure acting upward everywhere. And what's going to happen is your foundation is actually going to go through kind of a wave type response to that, a static wave where it just, gets loaded down at the column location, but in between them actually goes up and then goes down for the next one. So it would actually come up in between 2 columns and go upward a little bit. Not a real dramatic curvature on that, but curvature nonetheless. And with that upward curvature, let's call it, or concave downward, I'll call it, that kind of curvature, you're going to have tension on top. And that's why you may have steel on the top of a footing, by the way. And then we have development length in compression, which would be required in the vicinity of connecting to a column. And we'll get around to that with the design. But again, function of compressive strength of concrete, function of bar size, and function of steel strength. So it's just a matter of finding your way through these tables and saying, that's my parameter, that's my parameter, that's my minimum, that's my parameter. It falls into place quite readily, I'll say. I don't want to trivialize the content, but it does turn into somewhat of a cookbook type process. So looks like a good time for a break before we jump into the actual example problem. And let's do 10 minutes here. So let's say 3:12. We can get